keys, push the start. Yeah, you know what it is. Everything I do it big. Yeah, screaming that's nothing. When I pulled on the lot, that's nothing. I come to town, you see me, you know everything. Black and yellow, black and yellow, black and yellow, black and yellow. I put it down from the whip to my diamonds. I've been black and yellow, black and yellow, black and yellow.
My name is Haslina binti Hasan. In this lab report, we will focus on the application of Bernoulli equation to a hydraulic system. The experiment involved measuring the flow rate and pressure of water in a pipe with constriction, which caused a change in the fluid velocity and pressure. By analyzing the data collected, we will use Bernoulli equation to determine the pressure change that occurs in the system and the accuracy of the theoretical prediction. The report will also discuss the significance of Bernoulli equation in practical engineering application and the potential limitation of the model. The objective is to verify the Bernoulli principle when applied to the steady flow of water.
My name is Siti Nur Alia Mesara binti Rosidi, and I am going to explain the problem statement in this experiment. A real-world engineering problem related to the application of Bernoulli's equation is a design of municipal water supply systems. The problem is, how can we ensure that the water flows with adequate pressure from a reservoir to the residential homes, especially in high-rise buildings or hilly areas, without using too many pumps? The solution is Bernoulli's equation helps engineers to analyze pressure, velocity, and elevation changes in the water pipeline. In the Bernoulli's equation experiment, we study how pressure and velocity change along a varying pipe diameter. This stimulates real-life conditions in water supply pipes when a pipe narrows and rises uphill.
And hi everyone, today we will demonstrate the application of Bernoulli equation, an important principle in fluid mechanics. This experiment aims to verify Bernoulli's principle using a tapered duct when applied to the steady flow of water and to help us to understand the relationship between pressure head, velocity head, and elevation head in pipe flow. In this experiment, the parameters and variables that we're going to measure and obtain are diameter of the tapered duct, time taken to achieve 10 liters of water, distance tube point, and manometer readings.
This is the Bernoulli's apparatus. It consists of a horizontal duct with varying cross-sections connected to multiple manometer tubes. These tubes measure the pressure at different points along the flow path. The duct is connected to a water source with a control valve to adjust the flow, and we also have a measuring pen and stopwatch for a flow rate calculation.
Let's begin the experiment. So first, make sure the apparatus is level and the connection is tight. Over here, make sure there is no air bubble trapped in this manometer tube. And then over here, you can see there is diameter stated for calculation later. Switch and turn this valve so that the water will run. Wait until the water level reaches 0 and then start the timer. And then wait until it reaches 10, then we stop the timer. Let's run the experiment. For the first one, the water will increase slowly. The water already reached 0, so we start the timer and wait until it reaches 10. It's already reached 10, so we stop the timer.
Next, we record the water level in each manometer tube using the ruler. Before we take the data, make sure there is not air bubble trapped in the manometer tube. For example, for tube 1, the reading is 210, and then at the tube 2, the reading is 195, and then remove all the water in the tank and increase the flow rate for another data. Lastly, record and tabulate all the data obtained properly.
Hi, my name is Hasina Mahmood, and these are the results we obtained from the experiment, which we have organized in a table. Let's begin the simple calculation with Q1. We're going to start off with table 2. Over here, we get the volume in meters, so that we should convert it in meter cube, where we get the volume 10, but we need to convert it from meter to meter cube by dividing it with 1000. We also obtain time from the experiment, so we need to divide the volume in meter cube with the time, and then we get this for the Q1 and tube 1. Moving on to the table 1, we also get the diameter from the apparatus itself, but we need to convert it from mm to meter by dividing it with 1000. Same goes with distance tube 1 from cm to meter by dividing it with 100. Next, we need to determine the area, where from the diameter itself using the formula of pi d squared over 4. And then for the velocity, the q from table 2. The q from the table 2, we need to divide it with the area we obtain in the table 1. And then we get this answer. Moving on to the table 3. Pressure head obtained in experiment. We divided it by 1000. And pressure head 210 millimeter is equal to 0.210 meter. So we need to calculate the velocity head by using the equation of v squared over 2g. The v is from the table 1, and then we get the answer. For the last table, to determine the total head, we need to add velocity head with pressure head. Based on table 3, this we added with this one to obtain this. Finally, we obtained the full result for all 4 of this table. Following the final calculation, graph of velocity head against distance, pressure head against distance, and total head against distance were successfully plotted.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Haziq bin Muhammad Ramdan. Right now, I want to explain about discussion for this experiment. This experiment tests Bernoulli principle, which states that fluid speed increase if pressure decrease and vice versa. The principle applies to steady, incompressible, and frictionless flow. In this experiment, water flow through a tapered pipe. As the pipe narrow, the water speed increased while the pressure measured by manometer dropped a matching Bernoulli prediction. Since the water volume and time were fixed, the flow rate stayed constant throughout the test. For conclusion, the experiment confirmed Bernoulli principle in a tapered pipe. As the pipe narrowed, the fluid speed increased and the pressure dropped, matching Bernoulli equation. This showed that for steady, incompressible, and frictionless flow, the total energy, pressure plus velocity plus elevation stays constant along a straight line. This is example for Bernoulli equation. That's all from us. Thank you.